Hello and welcome to our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on a very important part of stoichiometry, which will be focusing on the limiting reagents as well as the percentage purity in the context of a chemical change or a chemical reaction. So that's what we're going to be doing for today. Now, let's look at the broader picture in as far as how limiting reagents actually fit into the broader quantitative aspects of chemical change. We want to also recognize that this still forms a part of stoichiometry, but our attention for this session will be on limiting reagents. Okay, so this is what it's all about. And remember, the mole becomes the SI unit of quantity of matter. So we'll talk a lot about the mole in terms of the balanced equations of reaction, but we also want to determine as to what exactly informs or determines the maximum amount of product that is formed based on the quantities of the reactants. As a result, we are saying this is about the quantitative aspects of a chemical reaction. Right. Now, these are the thoughts that are going to guide our discussion for today. Okay. The first question that we put is that what causes a reaction to reach completion? Okay, so when we talk about completion of a chemical reaction, is that as long as there is still a sufficient amount of reacting particles, the reaction will continue. Okay, so this is typically for a reaction that goes from left to right, from the products to the reactants in one direction. So when the reaction reaches completion, what is it that actually causes a reaction to reach that stage in as far as completion is concerned? So that's the big question that we want to put from the onset. So then again, the second one says, what determines the maximum amount of products in a chemical reaction? Okay, right. So those are the two questions. What are some of the keywords? Reactant, products, limiting reagent. When we say something is in excess, what exactly are we talking about? We also talk about the yield in terms of the product. So these two terms, they are actually related to each other. So if one substance is a limiting reagent, if one reactant is a limiting reagent, the other one must be in excess. So these are some of the key terms that we're going to focus our attention on. And on that note, we also want to put it out that, from the beginning that, the definitions, they form, an integral part of our scientific language. So us understanding the key words in a definition and using them correctly in context, I think it guarantees us, our full marks, because every long question will, one way or the other, carry a definition type of a problem. Right. Okay. Now, let's talk about something that we already know by this point. We're saying that the mole ratios in balanced equations. So everything is about the mole, which is the SI unit of quantity of matter, right? So in terms of quantity, or in terms of quantitative aspects of a reaction, we talk about the mole ratios. So a balanced equation of reaction actually tells us that this is the stoichiometric ratio, in which substances actually react with each other. So for us to quantify reactants and products, we have to talk to actually draw our attention to the balanced equation of reaction, which has a lot to do with the law of conservation of mass, right? Okay, and again, we also want to appreciate that the balanced equation of reaction is an indicator of the stoichiometric ratio. So the stoichiometric ratio in which substances react is actually, the whole number ratio in which these substances participate in a chemical change, which forms new substances, which are the products, right? And so when balancing the equation, we apply the law of conservation of mass. Okay, so if for argument's sake we consider a reaction that is simple hydrogen and chlorine gas to form hydrogen chloride, the stoichiometric ratio is 1:1:2. It means a mole of hydrogen reacts with 1 mole of chlorine to form 2 moles. So if we put this in terms of quantities or in terms of mass, we can say in 2 grams there is a mole of hydrogen. In 71 grams, there's a mole of chlorine, and so on. So this is the interpretation of the stoichiometric ratio in which substances react. Okay, so when substances react in any chemical reaction, when we talk about the limiting reagent now, okay, they do not necessarily react in exact amount that all reactants get used up. So in a way or the other, one of the reactants usually gets used up or exhausted, and then the other one remains. So that which remains is actually the one in excess. But the reactants that get used up is what would refer to the limiting reagent, which will actually determine the amount of the product, right? So this is what we want to appreciate also, that the ones that are not completely used up, they are in excess, right? And then also, as you know, that the limiting reagent can be used to determine the theoretical amount of the product formed. So that's the main idea in as far as the reagent is concerned, right? Now, I would quickly go to a simulation that would actually show us exactly what we mean when we talk of, you know, substances being in excess and the other reactant being, you know, a limiting reagent. Let's say, for argument's sake, a reaction between hydrogen and oxygen. If we've got 1 mole of that and 1 molecule of oxygen, you'd realize that there's no water that is formed. So unless we put a certain number of, you know, hydrogen molecules, there are 2 units of the products that are formed. So you'd understand that, but if we had 1 of each, there is no product that forms. So this speaks to the stoichiometric ratio in which they react. How about if we put 4 of these and let's say 2 of the oxygen? Okay, so the ratio still stands. It's 2:1:2. Because if you say 4:2:4, it's the same as the stoichiometric ratio in which they react with each other. So this is a typical example of what exactly it means when we say substances actually react in fixed ratios, right? So that's the main idea in as far as the stoichiometric ratio is concerned, right? Okay, so that's the whole idea in as far as, you know, the issue of limiting reagent as well as the reagent that is in excess. For now, we'll take a short break, and then when we come back, we'll look at questions that have to do with the limiting reagents in a chemical reaction. Let's take a short break for now. Welcome back. We're still looking into the limiting reagents in as far as reactions are concerned. So now we'll draw attention to typical examples. You know, we'll look at a scenario where 2 substances react with each other, and we may be given their, you know, initial amounts, and we need to decide which one of the 2 is in excess and which one is actually, you know, a limiting reagent. Because we've also appreciated the fact that these substances, they do not actually they are not actually placed, you know, in a reaction vessel, you know, in exact amount. So at one stage or the other, the reaction will reach completion or it will stop as a result of one of the 2 reactions being actually used up. Now let's look at a practical example, okay, involving, you know, limiting reagents. Now we are told here that we've got 192 grams of sulfur dioxide. So that's the mass of sulfur dioxide, which reacts with 64 grams of oxygen, right? These are the 2 reactants. They form sulfur trioxide as a product according to the following equation that's given to us. Which substance is the limiting reagent? So this is the actual question that we want to actually address. So let's go through the steps in terms of problem solving. What exactly do we need to do? First of all, because we know that to quantify matter in a chemical reaction, we have to talk about the mole as the SI unit. So in other words, it demands that we actually balance this equation of reaction. So as it is given, the reaction is not exactly balanced. So we'll try and apply the law of conservation of mass so that the reaction is balanced, so that we can derive the stoichiometric ratio in which these reactants participate in the reaction. So there's 1 sulfur on the left and 1 on the right. The problem comes with the oxygen. Okay, we've got 4 oxygen on the left and then 3 on the right. So for that reason, if we put a 2 here, okay, and we put a 2 there, okay, what does that mean for us? It says the sulfur is balanced. Oxygen, we've got 6, which is the 4 plus 2. There is the 4 and then the 2, which gives us the 6. So the stoichiometric ratio in which they react is 2:1:2, right? So we've taken care of the first part. However, we need to put it out there that sometimes the equation may be given already in balanced form, so you don't have to go through this. So pay careful attention to that. If it says a balanced equation of reaction is given, you know that part is sorted. But if it says an equation, verify whether the equation is balanced or not, so that we can arrive, you know, at the stoichiometric ratio in which the substances participate in the chemical change, right? Okay. Now, step number 2, we want to determine the moles of each substance, okay? Now, the number of moles of sulfur dioxide, okay, for argument's sake, is equals to mass of sample. The sample is 192 grams, okay, which is mass over molar mass. So the 192 is the mass of sample, okay? That's 192 grams. Now, if we go to our periodic table and try to get the molar mass of sulfur dioxide, we know sulfur is 32 and oxygen is 16. So what do we have here? We've got sulfur, which is 32, then 16 times 2, another 32. So this is actually 64 grams per mole, okay? So if we do this calculation, it will give us the exact, you know, moles present in that 192 gram sample of sulfur trioxide. So if we go to our calculator, it will give us 192, okay, which is the mass of the sample, divided by 64, which is the molar mass. In this case, it gives us 3 moles, right? So that's 3 moles, okay? There are 3 moles in the 192 gram sample. But then what about oxygen, okay? Number of moles of oxygen gas is equals to mass over molar mass. That's the formula, okay? So the mass of oxygen is 64, right, grams, divided by the molar mass of oxygen. So oxygen is actually a diatomic, you know, molecule. So it's, each one of them is 16 multiplied by 2. It gives us 32 grams per mole, okay? So the moles of oxygen, okay, in this sample is actually 2 mole, right? So we've taken care of that, right? And then moving along, it says here, step number 3, we want to use the stoichiometric ratio to determine which substance will react completely. So the balanced equation is 2 of sulfur dioxide plus a mole of oxygen to give us 2 moles of the product, which is sulfur trioxide. So how many moles of each? We've got 3 moles in the sample, okay? We've got 2 mole in the sample. So if we ask ourselves if they react in the ratio 2:1, okay? Now, for the entire 2 moles of the oxygen to react, we need, we need double the number of moles of sulfur dioxide, okay? So in other words, only because of these quantities that we have, what we're saying is that only 1 mole of oxygen will react, okay? And then if 1 mole of oxygen reacts, it must react with double the number, which is 2 mole, okay? So the question is, if this is the stoichiometric ratio in which they react, which of the 2 substances actually is the limiting reagent? Which one will get used up earlier because of the quantities that we have? So what we're saying here is that if the whole 3 moles of sulfur dioxide react, it will need to react with half that number of moles, which is 1.5 mole, okay? So in other words, what we are saying, the sulfur dioxide is actually our limiting reagent because the entire 3 mole of sulfur dioxide will react with 1.5. And then the unreacted amount of oxygen, which is in excess, is actually 0.5 moles, okay? So the 0.5 mole is what remains because of the 2 moles present in the 64 gram sample. Only 1.5 will react. It means all the 3 mole of the sulfur dioxide reacts, and then it means this is our reactant, which is the limiting reagent, and then oxygen is in excess, okay? Now, let's shift our attention to a different example that addresses more or less the same thing, okay? Which says here methanol, which is CH3OH, that's the formula of methanol, is used as a common fuel and can be produced, you know, from a reaction between carbon monoxide and hydrogen. So we're given the mass of the carbon monoxide, which is 356 grams, as well as 65 grams of hydrogen gas. Right, this is the equation of reaction. Now, we're also interested in determining which substance is the limiting reagent. So if one is the limiting reagent, it certainly means the other one is the one that is in excess, okay? Now, first things first, if we go through the very same steps that we did in the previous example, we would want to also check if indeed the equation of reaction is balanced or not, right? So the ratio, the carbon on the left, it's 1, on the right, it's 1, okay? Oxygen, it's 1, it's 1. Hydrogen, we've got 4, okay, on the right, so it means we need to put a 2. So what does that tell us about the stoichiometric ratio? It tells us that there is a ratio of 1 is to 2 is to 1. Okay, this is the stoichiometric ratio in which these substances react with each other, right? So first things first, we want to determine the number of the moles of each substance present in terms of the reactants, right? So the moles of carbon monoxide is equals to mass of sample divided by the molar mass, okay? So the mass of the sample is 356 grams. So we're asking ourselves, in 350 grams of the monoxide, how many moles are present, okay? So it's gonna be 356 divided by the molar mass of carbon monoxide, which is 12 plus 16. That gives us 28, okay, grams per mole. So that's grams, then that's 28 grams per mole, right? So that calculation will give us the moles of carbon monoxide, okay? So it's 356 divided by 28, okay? What do we get? We get that as a decimal fraction, 12.71, okay? So that's 12.71 moles, okay? 12.71 mole, right? And then what about the moles present in 65 grams of hydrogen, okay? So the mass of sample over the molar mass, right? So this sample has a mass of 65 grams, okay? There's 65 grams divided by the moles of the molar mass of hydrogen gas, which is 2 grams per mole. So that is from the periodic table, okay? So if we go to our calculator just to get that value of the moles, we get 65 divided by 2, okay? That gives us, as a decimal fraction, 32.5, okay? So that's 32.5 mole, right? Now, this is what it is. So from the balanced equation, 1 is to 2 is to 1, right? So we're asking ourselves, if these are the moles of, if we can rewrite that, so we've got carbon monoxide, how many moles are of there? 12.7 mole, okay? So we're comparing the moles there, plus 2 hydrogen, which gave us 32.5 moles, okay? This gives us CH3OH, right? That's the product. Now, the ratio is 1 is to 2, okay? This is the stoichiometric ratio in which they react with each other. So for every mole of carbon monoxide, we need double the moles of hydrogen gas. So if we've got 12.7, the entire 12.7 will react, or 12.7 mole of carbon monoxide will react with double that, which is 2 times 12.7, right? Okay, so as a result, all the carbon monoxide will actually be used up in the reaction, and then it becomes our limiting reagent. Now, how many moles of hydrogen will remain unreacted? Okay, that's the next question, right? So what is the mass of methanol that is produced? Maybe we want to start there. So if if we go back, we're saying 12.7 moles of carbon monoxide produces the same number of moles of methanol. So this is what it says in terms of those two, okay? So we have 12.7 mole, okay, of carbon monoxide, right, produces, okay, 12.7 mole of methanol, which is CH3OH, right? Okay, so that's the stoichiometric ratio because 1:1 from the balanced equation of reaction. Okay, so we ask ourselves, in 12.7 moles of methanol, what is the mass of methanol? We know that number of moles of CH3OH is equals to the mass that will be obtained over the molar mass of methanol, right? So the moles of methanol is 12.7, okay, is equals to the mass that we want to find, and then we can go to our periodic table and get the molar mass of methanol, which is 12 plus 16, which is 28 plus 4, which is 32, okay? So that's 32 grams per mole. So that's 32, okay? So if we isolate the mass, we'll get a mass of, if we can quickly verify that, 32 multiplied by 12.7, okay? So if we go to our calculator, we get 32 multiplied by 12.7, okay? We get that value as a decimal fraction. So the mass that will be formed is 406.4, right? So that's 406.4 grams of methanol that will be produced, right? Okay, and then the last part demands us what mass of the reactant is in excess. We need to go back. We know that 2 multiplied by 12.7 moles, okay, of hydrogen, okay, gas reacted, okay, right. But at the end of the day, we also need to ask ourselves, how many moles of hydrogen did we have? The moles of hydrogen that we have is 32.5 in the sample, okay? So if it's 32.5, so we have got unreacted, okay, is equals to 32.5, okay, moles minus 2 times 12.7, okay? This comes from the stoichiometric ratio. So if we quickly verify that, we'll have something like 32.5 minus 2 times 12.7. Okay, these are the actual moles that did not react. So we get 7.1 moles, okay? 7.1 mole of hydrogen, okay? So the mass is equals to mole over molar mass. We go back to that equation. So 7.1 is equals to the mass that we're looking for. Hydrogen is a mass of 2. So the unreacted mass of the reagent, which is in excess, which is hydrogen in this case, is 2.71, which is 14.2 grams. So that's the whole idea in as far as the calculations are concerned. Right. Hopefully this makes a lot of sense in as far as, problems involving the limiting reagents, the reagents in excess. You need to do as much practice as you possibly can. All the best with that. now let's focus our attention on something that's very relevant in as far as quantitative aspects of chemical change, which has to do with purity. Sometimes we would express this purity in terms of a percentage in the context of, reactions that involve, substances that have got impurities. So what exactly is purity all about? Some of the key words that we would want to actually pay careful attention to is purity, which also we've indicated that we can express it as a percentage. But in what context is, purity relevant in as far as the chemical reactions are concerned? Okay, so we know that most samples of substance, they contain impurities. Now, if you ask yourself, the most important question, that what are impurities? Suppose you've got a substance, when you find it, in the manner in which it occurs, it's not 100% that pure substance. It may have some other substances which are not exactly, the main, substance. As a result, we'll say that this substance is impure. This could be, in the context or in the example of mineral ores. When you purify minerals, especially, say, in the mining sector, they actually try to get rid of the impurities so that at the end of the day, we remain with the actual substance without these impurities. So in terms of the pure substance in the sample, as expressed as a percentage in terms of the total mass, that gives us a percentage purity of a substance. So we want to think of it that way, right? So these samples, they contain impurities. Minerals, they contain impurities even after the refining process. So the mass of the pure substance can be expressed as a percentage of the whole sample. This is what gives us the percentage purity, right? So it's a simple and straightforward question, but concept. However, it is understood in the context of chemical reactions. So how do we calculate percentage purity? It's actually the mass of the pure substance in the sample divided by the mass of the sample multiplied by 100. So this is the mathematical, equation that we use to determine percentage purity of a substance, right? So how exactly do we determine percentage purity? Given the mass of the sample or the impure reactant, why is we saying reactant? Because it could be in a chemical reaction, okay? So we need to complete a chemical reaction and measure the mass of the products formed, okay? So the product is assumed to be 100% pure, right? And then we can carry out the stoichiometric, now working backwards, the stoichiometric calculations to actually find the mass of the pure reactant based on the mass of the pure product. And then a comparison is made, between the mass of the reactant to the mass of the pure, product as a percentage. Okay, so that's as far as how we determine percentage purity. Here's a simple and straightforward example just to give us an idea of what we mean when we say, okay, these are the steps as to one that needs to follow in as far as calculating percentage purity. We've got a sample of eggshells, okay? So eggshells, they contain, calcium carbonate. They contain calcium carbonate and other substances. Okay, so we are interested in determining, the actual percentage of calcium carbonate in the mass of the whole sample. So the total mass of the sample is 5 grams. It's heated at a temperature of 100 degrees Celsius, and it decomposes. What does this tell us? It tells us that this is a decomposition type of a reaction, okay? So step number 1, we need to balance the equation of reaction. How many atoms of calcium do we have on the left? It's 1, 1. Carbon, it's 1 on the left, 1 on the right. Oxygen, we've got 3 on the left, and then 3 on the right. So this is actually balanced, okay? So the stoichiometric ratio in which they react is 1 mole of calcium carbonate decomposes to form a mole of carbon dioxide and a mole of calcium oxide, right? So if the equation is balanced, then we measure the moles of carbon dioxide formed, okay? The moles of carbon dioxide formed in this case, we are saying that if 5 grams is heated, so how many moles of calcium carbonate are there in the 5 gram sample, okay? So number of moles of calcium carbonate, okay, is equals to the mass of the sample over the molar mass, okay? So we'll determine the number of moles of calcium carbonate in the sample. And then we are also told that we need to measure the moles of carbon dioxide, okay, that is formed. So if we have the moles of carbon dioxide that are formed, okay, whatever that is, we'll try and work backwards to say how many moles of calcium carbonate actually produced this mass of this moles of carbon dioxide, and then actually get to a point where we are able to determine the actual percentage of of calcium carbonate in the sample of the eggshells. So step 3, and then we work backwards, we determine the mole of calcium carbonate needed to release that amount of carbon dioxide, okay? So it's like we working backwards, but the idea is, the idea of number of the moles of substance equals to mass of sample over the molar mass is what is central here, and the stoichiometric ratio of 1 is to 1 is to 1. So we would ask ourselves to say a mole of calcium carbonate produces whatever number of moles of carbon dioxide. So given the moles of carbon dioxide, we can work backwards and determine how many moles of calcium carbonate were responsible for producing that amount of carbon dioxide. And then we can, after that, we can determine the mass of pure calcium carbonate in the sample. So at the end of the day, percentage purity of this sample of calcium carbonate is equals to mass, okay, of calcium carbonate, okay, in sample, right, divided by total mass of sample. All right? Okay, as a percentage, we multiply this by 100. It will give us the percentage purity, right? So that's the main idea in as far as, determining the percentage purity of a substance. For now, let's take a short breather. When we come back, we'll try and look at a practical example with the actual masses of samples and try to determine, the percentage purity using, real substances and real, masses, and try to work backwards in as far as the stoichiometry is concerned. Let's take a short break for now. Okay, now let's look at a practical example in as far as percentage purity is concerned. It says here a sample of table salt, which is the actual substance that we are interested in, is contaminated by sand. So it means sand is our impurity, okay? This is our impurity, right? So table salt, which is the pure substance, sodium chloride, okay? So the mass of the sample is 5.5 grams. So this is a very useful piece of information because this is actually the total mass of sample, okay? Pay careful attention to that. So the sample is dissolved in distilled water and filtered, okay? So the mass of the residue is 1.5 grams. So the residue in this case is the mass of the sand, which is actually insoluble in water. So all the table salt will dissolve in water, and then what will be filtered off is actually the impurity. So in as far as calculating the percentage of table salt, this is how we would actually go about it, okay? So we know that percentage purity, okay, is actually equals to mass of sodium chloride, which is table salt in this case, okay, in sample, right, and then divided by total mass of sample, okay. So this is typically multiplied by 100, right? So this is typically a routine type of a question where you identify the correct formula, do the necessary substitution, and then find the correct answer, okay? So the mass of sodium chloride in the sample is actually total mass of the sample less that of the impurities, which is actually 5.5, okay, minus 1.5, okay, divided by the total mass, which is 5.5 grams, multiplied by 100, okay? So the percentage purity then becomes, if we go to our calculator, what do we have? 5.5, we can even punch it like straight into the calculator. 5.5 less the mass of the impurity, which is 1.5, divided by the total mass, which is 5.5. We multiply that by 100. Okay, then this will definitely give us the percentage purity. So the percentage purity of table salt is 72.73, right? So it's 72.73%, right? Now, always leave your answer to 2 decimal places unless or otherwise specified, right? Okay, now let's look at a different question altogether, still addressing percentage purity of a substance. It says here, a learner heats 50 grams of calcium carbonate, okay, which reacts according to the following balanced equation. So what's the main idea here? It's not always that you'll be required to balance. Sometimes the balanced equation of the reaction will be given to you. So that part of the law of conservation of mass has already been taken care of. So yours is to actually apply the stoichiometric ratios, to try and check, the percentage purity in the actual substance that we are looking at. So calcium carbonate decomposes to give us carbon dioxide and calcium oxide. So if this is balanced, it says to us the stoichiometric ratio in which they react is 1:1:1, right? Okay, so what mass of carbon dioxide will be collected if the calcium carbonate was 100% pure? Now, we are saying that if it's 100% pure, we are saying that in that 50 grams of calcium carbonate, there is no impurity if it's 100% pure. So there is 0 impurities. So all that 50 grams is actually the pure substance, which is calcium carbonate, right? So that's the first question. Now, how then do we answer that? We will use our stoichiometric ratio. So we know that the ratio is 1:1, okay, because we were interested in the carbon dioxide gas that will be collected. So we ask ourselves whether how many moles of calcium carbonate are present in 50 grams. So now the moles of calcium carbonate present in 50 grams is mass of sample over the molar mass, right? The mass of the sample is actually 50 grams. It's given. Molar mass, if we go to our periodic table, we will get, calcium has a mass of 40, okay, plus the mass of carbon, which is 12, and then plus the mass of oxygen multiplied by 3. So it's 3 multiplied by 16. So this gives us the molar mass of calcium carbonate, which is 100 grams per mole, right? So that's 100 grams per mole, right? So in other words, if you do that on a calculator, you get half a mole, which is 0.5 mole, right? So 1 will produce 1, meaning 0.5 mole, okay? 0.5 mole of, calcium carbonate. Okay, that's the most important part. Will produce 0.5 mole, okay, of carbon dioxide gas, right? So we're asking ourselves, what is the mass of a 0.5 mole sample of carbon dioxide? Now, we'll say then moles of carbon dioxide, okay, is equals to mass that will be obtained divided by the molar mass. So the mole is 0.5 because of the ratio 1:1, okay? So we're looking for the mass. But what's the molar mass of carbon dioxide? It's 12 plus 16 times 2, okay? Which gives us, just to verify that, 12 is for carbon plus 16 multiplied by 2, okay? That gives us a 44, right? That's the molar mass of carbon dioxide. So that's 44. So the mass of carbon dioxide that will be collected, if that was 100% pure, is equals to 0.5 times 44, which is equals to 22 grams, right? So this is what the question demanded of us, okay? Right, the follow-up says, the learner collected 18.2 grams of carbon dioxide gas. Calculate the percentage purity, okay? Now, if we expected 22 grams, but instead of the 22, we only collected 18.2 grams. So percentage purity okay, of the calcium carbonate, okay, is equals to mass of carbon dioxide, the actual mass of carbon dioxide, okay, collected, okay, divided by the theoretical one, which is the one that we got, which is, or the expected one, okay, mass of carbon dioxide, the one that we calculated using the stoichiometric ratio, we multiplied that by 100. Okay, so the actual mass is 18,2, right? We expected it to be 22, right? And then we multiply that by 100. This will give us the percentage purity of the calcium carbonate, right? So in this case, what do we have? We've got 18,2 divided by 22. We express that as a percentage times 100, okay? What does that give us? As a decimal fraction, is 82,73, right? So the percentage is 82,73%. We always express it to 2 decimal places, okay? Now, the question then goes further and says, what mass would have been collected if the sample was 70% pure? Now, what we are saying, if it was 100% pure, it would have expected 22 grams, okay? So 18.2, we can use a stoichiometric ratio. So this is more of a question that involves ratio and proportion. So we are saying that of the 50 grams sample of carbon, so calcium carbonate rather, only 70% of that sample is actually the pure substance that we are interested in. Now we're asking ourselves, what will be the mass of carbon dioxide that will be collected, right? So if we go back to the previous one, at 82%, 82,73, okay, we got only 18.2, okay? So if it was 70, what would be the new mass that will be collected? So 82,72% purity will give 18.2, right, grams. What about 70%? Okay, it gives, we can model this and say X. Okay, so the question here is that are we using the same mass that we are given, which is 18.2? So if we get that, we are able to determine the mass, which is X in this case, is equals to, we can kind of cross multiply that, which gives us what? 70 multiplied by 18.2, okay? By 18.2, okay? So this is just simple math divided by 82,72, right? Okay, so if we go to our calculator, just to verify that, we'll have 70 multiplied by 18.2, okay, divided by 82,72, okay. But this is just one of the ways of doing it, okay? There are many ways in which, so if it was 70%, we'll get the mass that will be collected is actually 15,4, right? So it will be 15,4 grams of carbon dioxide gas that will be collected, right? Now, this is the main idea in as far as that, okay? So we've done that calculation. So it means that if we're saying that this 50 grams contains impurities, it means a particular percentage of that 50 grams is actually calcium carbonate, and then the rest of that mass actually consists of the impurities, right? So this is the main idea in as far as percentage purity is concerned, right? So there will be many different examples that you'd want to actually use in as far as, calculating percentage purity, but you must take note that the balanced equation of reaction actually gives us the stoichiometric ratio. Now, if we're saying if it's 100%, it gives us a certain mass, okay? We would use that fact to actually say that, okay, if the sample contained a percentage that's less than 100 of the actual substance, then what is it that will be actually formed? So we try and be flexible around that, but more and more practice in this will definitely go a long way in terms of understanding what percentage purity entails in as far as, problem solving is concerned. All the best with that.